Let's think about some more intermolecular forces with an kind of interesting situation. So a new factory has been put up that is dumping its wastewater into a local river. At first, this seems harmless because it is clean, fresh water. It's just condensed from steam, so it checks out. There's no pollutants or anything. But all of a sudden, downstream, you end up with a bunch of fish dying, but there's no pollutants. The one difference between the water that's already in the river and what's coming out of the factory is it's a lot warmer. So all that heat helps to move out something very important from the water, which the fish and other aquatic life need. That's oxygen. We actually have some oxygen dissolved in most water that we deal with, and that's kind of an important thing for fish. Fish we sometimes think about as breathing water, but it's less of that and more of extracting the oxygen that's in the water. So we have oxygen molecules kind of tucked away in between water molecules, and that's what the fish kind of use and extract as they pass the water through their gills. So if your water gets a little too hot and the oxygen is able to move its way out and escape from the water, then there's nothing really in the water for the aquatic life to breathe and extract from there. So if we back this up a little bit, what is keeping the oxygen in the water in the first place? I mean, if it's a gas at room temperature, you'd think it would just fly on out. And apparently, if you give it a little bit of energy and get it to a higher temperature, then it can work itself out. But at room temperature, what's keeping it in there? So it must be some kind of intermolecular force between the molecules. So let's think about what those molecules look like. So on the left here, I have water, H2O, and on the right, I have O2, dioxygen, a diatomic molecule of two oxygen atoms. Okay, water has a permanent dipole. In other words, it's always polar just by the nature of it. Because oxygen is more electronegative, it pulls the electron cloud more towards it and away from the hydrogen atoms down here, which are less electronegative. So you end up with partially negative charge up top. You've got a little partially positive charge down by the hydrogens, and therefore a dipole across the molecule. Okay. On the other hand, oxygen, O2, is nonpolar. These two atoms share their electrons pretty fairly. They're both pretty electronegative, but since they're pulling kind of at the same sort of force either way, the electrons are pretty fairly shared across here. So we have no dipole. Okay, at least for the moment. When we go and put oxygen in water, we get something like this. So we have a water molecule with its permanent dipole here, and it's partially negative charge, and we've got a molecule of oxygen that is nonpolar. But kind of like in dispersion forces, we can bully an electron cloud into moving around. If water can kind of get and mosey up to an oxygen molecule like this, the partially negative side of a molecule of water can push on the electron cloud of this oxygen molecule and kind of scooch the electrons farther away from this partially negative side. They can repel each other. So the electron cloud can kind of drift over to the right a little bit. We can also have the opposite situation where the partially positive side of a water molecule moseys on up to an oxygen molecule and says, ooh, I'm going to start pulling your electron cloud towards me. My partially positive charge is going to attract the negative charges of your electrons in your electron cloud. And so the electron cloud moves this way. Okay? In either case, what we get is something like this. We are left with more partially positive charge over on this side. Partially positive. And our electron cloud is drawn more towards the right side of the molecule, something like this. This is maybe a little dramatic, but gets the point across. We got our partially negative side there. And what we make here is a temporary dipole. Again, something that we saw with dispersion forces, except in those cases we call it either instantaneous or induced, depending on the situation. In this case, the dipole has shown up by the pushing and pulling of another. In this case, since we have forced this to become a dipole using an existing permanent dipole, This is a temporarily induced dipole. So we've used a dipole to induce a dipole. Therefore, this intermolecular force, this intermolecular attraction between these two molecules is called a dipole-induced dipole intermolecular force.